Okay, today we're going our talks with regards to filters by talking about second order filters. And I believe I mentioned on Monday, no, second crap, thank you. I would have been back. Second order filters can be used to generate low pass filters and high pass. We're going to skip those and go straight into band pass and band stop filters because they're really more ideal. All right, so let's start with this guy. Let's see. Oops, that's not the color. Second order passive filters. All right. All right, sorry about that. The connectivity here on campus just got wonky. All right, so circling back around. Let's say that we have an inductor in series with a capacitor. We have a resistor like so. And we use this series RL.
Screen sharing.
I'm not screen. Okay, thank you. Can you see it now?
Yeah.
All right.
Yes.
Thank you. We have an impedance J omega L for our inductor, an impedance 1 over J omega C for our capacitor, and an impedance of R for our input terminals on the left-hand side, our output on the right-hand side. So this is just a series RLC circuit being used as a filter over just the resistor. All right, so our transfer function, oh, my internet is unstable again. Just using the principle of voltage division. In my denominator, I'm going to have R plus J omega L plus 1 over J omega C. And in my, I'm going to have R. I'm going to multiply by J omega C. And this gives me 1 minus omega squared LC plus omega RC in my denominator and a factor of J omega R in my numerator. So this is my baseline, easiest representation of my transfer function for this guy. Go through the steps as we've done previously, finding the magnitude response or the frequency response. So just finding the magnitude function. We'll also find the phase response, and then we'll identify some specific frequencies of interest. So for our magnitude, we are going to continue manipulating this transfer function equation, separate it into a discrete real portion and imaginary portion. So if I take that complex number and I multiply it by the complex conjugate of the denominator, what I will get is in my denominator 1 minus omega squared LC quantity squared plus omega RC quantity squared. And I'm going to have a real part of omega RC squared plus J RC times 1 minus omega squared LC. And lastly, just splitting things up, omega R squared plus J minus omega squared LC quantity squared plus omega RC. And over here, omega RC times 1 minus omega squared LC. So this is still my function, but now I've expressed it as a rectangular and I can easily determine the magnitude response, phase response from this equation. So for our magnitude, the magnitude of h of omega is the square root of the real part squared plus the imaginary part squared this whole thing, which is going to result in, so let's just kind of do some stuff in our head real quick here, right? So we are going to have a factor of omega RC quantity squared that is common to both that left-hand term and that right-hand term. So I'm going to say that we're going to have omega RC quantity squared multiplied by omega RC quantity squared plus 1 minus omega squared LC quantity squared divided by 1 minus omega squared LC squared plus omega RC squared, this whole thing squared. We can see that this term exactly cancels out 1 power of that guy. And we are left with divided by 1 minus omega squared LC squared omega RC squared. One just point here that I'd like to make, some texts write slightly differently. Instead of having 1 minus omega squared LC quantity squared, they write it as LC minus 1 quantity squared. They're the exact same things, because when you take the difference of those two guys and square it, it doesn't matter if the result was positive or negative. So they represent the same thing. Don't think I'm teaching you wrong because one particular textbook uses omega virtually identical. This is our, so what happens if omega is equal to 0. What is the of our magnitude response when omega is 0? 0, right? What happens when omega approaches infinity? So at very high frequencies. I disagree. Oh, I'm sorry. I should have a square root sign here. I apologize for that. It's also going to be 0. We're going to have infinity over, or sorry, over infinity squared, which will be 0. Okay. So that may not be super obvious. There's a little bit of a potential question here. So there's another way that I would like to think about this, all right? At omega is equal to 0, what is happening to the impedance of the capacitor? So omega is equal to 0 implies it's a DC circuit, right? So how do we treat a capacitor in a DC circuit? It's an open circuit, right? No, if we replaced our capacitor with an open circuit, no would be passed the source on the left-hand side. No current would flow through our resistor at all. So the output voltage has to be 0, right? At very, very high frequencies to the inductor. The inductor is the part that becomes the open circuit, which means the could go to 0. Okay, so that might be a little bit easier way to interpret what's going on at high frequencies and low frequencies. So I'll just put in the notes here, capacitor is open circuit. And here, the inductor, playing the role of the open circuit. Low frequencies, 0 for very high frequencies, but it's not 0 everywhere. What value of makes h of omega equal to 1? Any thoughts on how we might figure? So fundamentally, what does it mean if the magnitude of our transfer function is 1? Of our transfer function is 1, that means that V out is exactly equal to V in. All right. So we are trying to figure out what frequency causes that to occur. But we can look at this circuit qualitatively and kind of figure something out, right? So if we want V out to be exactly equal to V in, what does this impedance J omega L plus 1 over J omega C need to look like in order to make that happen? They have to cancel each other out so that they have to look like a short circuit, right? If we replace the inductor and capacitor with a short circuit, then V in is the voltage drop over the resistor, which is exactly equal to V out. So we need J omega L plus 1 over J omega C to be equal to 0. Which, if we multiply by J omega C, both sides by J omega C, this becomes 1 minus omega squared LC is equal to 0. And from this, we're going to give this guy a special name. Omega naught is equal over the square root of LC. So our filter here has a center frequency or resonant frequency 1 over LC. Is it surprising for the square root of LC? Does this value surprise you at all? Race, you're shaking your head no. Why not? You're exactly right. This is the exact same as the resonant frequency series LC circuit, and that's exactly what we have. It's just a simple series RLC circuit. Okay. So it's 0 for very low frequencies, 1 at resonance, and then trails down to 0 again for very high frequencies. There are, in this case, 2 3-decibel frequencies that we need to account. And so what I mean by that is I'm going to draw a quick picture of roughly what's going on here. So this is our map. Here is omega, and I'll do it in blue. So we have something like this. This value is 1. So I'm going to say this value right here is 1 over root 2. Our peak value occurs at omega naught. And we have this guy over here, which we're going to call omega low. And this guy right here, which we're going to call omega high. And just for thoroughness' sake, I'm going to go ahead and define another quantity called the bandwidth, which is simply omega high minus omega low, because that is the width of our pass band, right? Because everything outside of that we consider to be attenuated or rejected, and everything inside of that is passed. All right, so omega low is negative r over 2L plus the square root of r over 2L quantity squared plus 1 over LC. Okay. I didn't derive this because I don't really need to. We're just going off of how this guy is effectively a second order RLC circuit here. We can, from this, really say that R is negative alpha plus the square root of plus and our high frequency omega is positive r over 2L plus 2L squared plus 1 over LC alpha plus the square root of alpha squared plus, I'm skipping 7 minutes worth of algebra to get to more. All right, so here we have low and omega high. So I ask of you guys then, how can we express our bandwidth in terms of our component values? Any thoughts? So I have a common factor of plus the square root of all that jazz on both sides. So those guys are going to cancel each other out, right? So R over 2L minus R over L as my bandwidth. Easy enough to figure out. So this is how we can design a bandpass filter for a specific frequency. So I had mentioned that I'm going to have you guys do this as a simple design project. So let's kind of talk about those constraints just real quick. I'll formalize it in a document. Who knows what the operating frequency of Louisiana Tech's radio station is? KLPI. 89.1 megahertz, right? Your design project then, omega naught is going to be 2 pi times that frequency, because that's the center frequency. That's the one we want to most strongly idea of what the of an FM radio signal needs. This is probably not as obvious. So if you're sitting at a frequency of 89.1 and you turn your radio dial 1 notch to the right, what's the next station that you would direction? It would be 88.1, right? So that means radio station is centered at a specific frequency and has a 0.1 bandwidth to the left, gigahertz bandwidth to the right, starts interfering with the next station. So the overall bandwidth is then 200.200 kilohertz. So from there, if you know what the bandwidth is and you know what your center frequency is, it should be components to work everything out, because you know the relationship for your bandwidth is R over L, and you know what omega low is, which tells you what C needs to, or you know what omega low and omega high is. Excuse me, help you figure out what C is. So it's all just ratios of components to build a receiver that picks up specifically that one station. So, all right, our frequencies of really, we have all of our frequencies of interest defined here. For those of you who were on Zoom and it died or whatever, we defined our bandwidth, our low frequency, and our high frequency, and our center frequency, all that kind of good stuff. So the last thing that we have to talk about for this particular filter, what should be obvious by now is a bandpass filter, is our phase response. So theta as a function of omega is the arctangent of the imaginary part. So let's scroll up here. The imaginary part was omega RC times 1 minus omega squared LC divided omega RC quantity squared, and we're left with the arctangent of 1 minus omega squared LC over omega RC. All right, so that's our bandpass filter. Let's take a moment quick to look at how we can use Mathcad to. Okay. This is Mathcad. When we're plotting things, as I was mentioning to those of you who are physically present, it kind of freaks out if we use units. So I'm just going to choose an arbitrary resistor value of 1. and an inductor value of 1, and a capacitor of 1. And I'm just going to write a simple equation. H as a function. All right, Zoom dropping out is getting ridiculous. So what we're doing right now is that we're going to use Mathcad to do some stuff before I get pissed off and leave. So the question that I was just asked, just for those of you who are interested, I was able to type, let me do it again just for the sake of argument, assuming Zoom doesn't drop out. I typed H and then the letter W, and you can convert that letter to omega just by hitting Control G, which converts any normal or Roman letter or whatever the hell you want to call it into its Greek equivalent. So shift equal sign, and now I'm just going to put in my transfer function equation from what we got at the very, so J times omega times R times C divided by 1 minus omega squared times L times C. Oops. Plus J times omega times R times C. All right. So to use Mathcad to view both the magnitude response and the phase response to kind of check things, what we can do is a plot. So I'm just going to drop an XY plot into the page here. And it's got two for us to put things. So on my Y-axis, I want to plot, just try to do H of omega, I believe, and let me put omega down here. We'll freak out. Yeah, and it's giving me nothing. The reason why it's giving me nothing is because it doesn't like the fact that there's an imaginary number in there. To plot it, I need to put an absolute value around it. Now I get something, okay? But this plot is actually a pretty bad plot, and the reason why I say that is it's because it's accounting for negative frequencies as well. So if I click down here on my x-axis, should allow me to change my numbers. So let's look at this guy up to 100 hertz, and I'm going to change my left thing to 0. And now we're only seeing from 0 to 100, but it still looks a little bit wonky. So while I have my x-axis thing selected, I'm going to go over here and click the logarithmic scaling button. And now we can see our bandpass filter response. It's not as pretty as LT Spice's because I don't know how to force it to put 1,000 points per decade and all that kind of stuff like I do in LT Spice. I'm sure there's a way to do it. But this is just a quick and dirty way to verify some things. One thing, if we plotted this current guy on LT, so let's take a moment to do that. Let me get my have a resistor, an inductor, and a capacitor. 1 Henry, no series resistance, although the resistor value is large enough it shouldn't matter. 1 farad, 1 ohm. No, wait, I don't need a diode, I need a voltage. Doing my AC analysis, so I just put my AC amplitude as 1. Need to throw ground here. AC analysis, going to do decade, 1,000 points per decade. Start it at 1 milli, end it at 1K. It's out of the way. The center frequency of this guy, we can easily see is not 1 hertz, which is what we're getting on our Mathcad screen. And it's because, again, LT Spice does everything in terms of frequency. So we need to correct this by putting a factor of omega over 2 pi. We'll express this as a function of linear frequency. And there we go. It's now centered over the same thing. If we wanted to make a true one-to-one correlation between the Mathcad graph and the LT Spice graph, we need to, instead of just plotting the magnitude, we need to plot the 20 times the logarithm of the magnitude, or express it in decibels. And log, hold on, open parentheses, absolute value, H, open parentheses, omega. There we go. And now my left-hand axis is expressed in decibels as well. So we can see that these guys match up. Looks like a fairly linear line on the decibel scale. For our phase response, if we wanted to plot that in Mathcad, the ARG function takes the argument of a complex number, and the argument of a complex number is simply its polar angle. So the argument of omega is going to give me this, where my left-hand axis is expressed in radians. And so to fix that, I just need to literally type DEG in for the units with the correct unit. At that, so it's starting off at around 90. At the resonant frequency, the phase angle is 0, and then goes on and so forth. And exactly what we're seeing. It starts up here at 90 degrees at resonance. It is 0 degrees, and then continues along. And we for mathematical equations that we and plot them. So yeah, I can't give you a good reason other than it's what I want, and I'm your teacher, so do it that way. What? Yeah, that too, sure. Yeah. Consider it like your boss is giving you a specific format to do something. So, all right. So what I was saying before Zoom crapped out for the 14th time or whatever, is that you can use Mathcad to check your answers by typing in an equation for the math response and then plotting that while also plotting the magnitude of the transfer function and then comparing them. It should be a 1-to-1 ratio, exactly like what you saw for the when you were determining whether or not your transient wanted to bring that up as another sure you're doing your homework correctly and all that jazz. The reason why I mention that is because some of the problems that I'm going to give you are going to require significant mathematical manipulation, and it's easy to make a mistake. So I just want you to have a means by which you can say, okay, so when I do this simplification, I didn't screw up. And when I do the next iteration of simplification or something, I didn't screw up, trying to figure out the magnitude. And I don't remember the name of it off the top of my head, but there is a online website that can simplify complex number fractions. And to be honest, I would prefer that you just use that and save yourself the trouble of writing 4 pages of algebra responses me. So I'll put a link to that in the homework assignment so that you can save yourself a ton of headache. I swear, if you die on me again, Zoom canceling the rest of class. It's ridiculous. All right, so let's circle back around and look and stop filter. We're going to go through this relatively quickly because so much of the material is literally the exact same thing as our band pass filter. So to realize a band filter, instead of taking the output over the resistor, we now take the output over the inductor in series with our capacitor. J omega L and 1 over J omega C plus minus V in plus minus V out. And it's actually kind of interesting why this works. So if we took the output just over the inductor, we would wind up with a high pass filter. And if we took the output just over the capacitor, we would wind up with a low pass filter. So effectively what we're doing is we're taking the output of a high pass filter in series with a low pass filter and mixing them together to create a band stop filter. All right, so our transfer function H of omega is going to be J omega L plus 1 over J divided by R plus J omega L plus 1 over J omega C multiplied C over J omega C gives us 1 minus omega squared RC divided by 1 minus omega squared. Oh, sorry, that's not RC, that's LC. Omega squared LC plus J omega RC. All right. So if I wanted to break this into a rectangular form complex number, I would simply multiply by the complex conjugate denominator. Doing so, I get 1 minus go away thing omega squared LC quantity squared minus J omega RC 1 minus omega squared LC over 1 minus omega squared LC quantity squared plus omega RC quantity squared. So numerator, our magnitude is going to be the square of the real part. So that's this guy plus the square of the imaginary part. And skipping one step just because I don't want Zoom to die on us again, we get omega squared LC divided by the square root of 1 minus omega squared L quantity squared plus omega RC quantity squared. When omega is equal to 0, magnitude is 1. When omega is equal to infinity, the magnitude is 1. So we're going to have something that looks like this. Where middle here we have omega naught, and then if this guy is 1, let's put 1 over root 2 right here. So this is omega low, this is omega high, and the exact same numerical values for omega naught, omega low, and omega high from the bandpass filter. Omega naught is 1 over the square root of LC. Omega low is negative R over 2L plus the square root of R over 2L squared plus 1 over LC. And omega high is positive R over 2L plus the square root of R over 2L quantity squared plus 1 over LC. All right, last, the bandwidth then is omega high minus omega low is still simply R over L. And the last thing we need is our phase response. Theta as a function of omega is going to be the inverse tangent of the imaginary portion divided by the real portion. So that's going to be negative omega RC divided by 1 minus omega squared LC. All right, finished it before Zoom died. Again. We could throw this guy into Mathcad, LCS, whatever, look at it, blah, blah, blah. It's all going to be the exact same thing as we just did, just inverted, right? Where we had our peak, we should now see that we have our minimum values. Where it was at our minimum values, we should now see our peaks. So it's literally just the high pass, or excuse me, the band pass filter flipped upside down. All right, so that's enough out of me for today. Your take-home portion of exam 2 today by 5 p.m. I'm just figuring out one of the 3 problems that I want to ask of you. It will on Wednesday. So that means you have Saturday, Sunday, Monday, Tuesday, Wednesday, 5 days to do it. I feel like 5 days to work 3 problems is reasonable. There will also be a homework assignment on filters posted today, probably sometime around midnight after my wife goes to sleep, so I can make out some new, won't yell at me for getting up and doing some work. That will be due 1 week from today. We are going to start on 3-phase power today. I would prefer if you were all actually physically here for the first day of 3-phase power, just because we're going to be talking about an awful lot of nomenclature that is typically confusing to students. And I feel that since I never see questions in Zoom, it would be better if you were here so that if something doesn't make sense, you can actually ask a question of me and we can spend some time explaining it. Because if you don't understand all this terminology stuff that we're going to be dealing with on the first day, you're going to be so wildly lost for the entire rest of the class. It's really, really important to fundamentally understand what it is I'm talking about and what it is I'm asking for in 3-phase circuits, or none of it makes any sense. Okay, so I will see you guys on Monday.